Hello, this is the Layers of the Earth presentation. So in our assignment on the layers of the Earth, we're going to go ahead and start and go through this. We're going to talk about the layers of the Earth and how we know that. This is Dr. Stern. So here in number 1 in your document is what shape is the Earth? And the Earth is actually not a perfect sphere. It's a spheroid. It's an irregularly shaped ellipsoid. And actually number 2, does the shape of the Earth change? Yes, it changes constantly. And can you think of some reasons why that may be? In your assignment, it asks for 2 things. Possibilities might be rebound of the crust after glaciers melt. The tides, of course, shift the oceans and where they are from high tide, low tide. The plate tectonics make the plates, the continental lithosphere, drift around. Erosion. There's all different things at all different scales that make this irregularly shaped ellipsoid change shape. So in this slide right here, we're in number 3, fill in the table with the Earth's layers. And here you have the crust, which is a very thin crust at the surface. And that crust in the oceans is about 5 kilometers thick. In the continents, it's about, on average, 35 kilometers thick. It is solid. It's like the rocks that we build South Lakes High School on, that we walk around on. The mantle is right below the crust in the gray on this slide. The mantle has one part of it that's actually partially liquid, a very small amount, and that mantle extends from 30 kilometers deep down to about 2,890 kilometers deep. Then we get to the outer core here. So that mantle is that pink part, that gray part. The inner core and the outer core. The outer core is actually completely liquid iron. It extends from 2,890 kilometers deep to 5,150 kilometers deep. And then we have the inner core, which is solid, extends from 5,150 kilometers to about 6,370 kilometers. So the depth of the Earth from the surface to the center is about 6,370 kilometers. All right, number 4 in your assignment. What are 2 zones noted in the diagram? So we have the layers, the crust, the mantle, the inner core, and the outer core. But there are 2 zones, if you notice on the picture to the right, the lithosphere and the asthenosphere. The lithosphere is solid. It incorporates the crust and a little bit of the upper mantle, completely solid. The asthenosphere is the part of the mantle that has a small amount of liquid in it. It allows those lithospheric plates to slide over them and move around on the surface of the Earth. Number 5 in your assignment. What layers does the lithosphere include? It includes the crust and a part of the upper mantle, as shown in the upper right-hand side right here. Here's the crust and a little bit of the upper mantle in gray incorporated in the lithosphere. The asthenosphere is completely in the mantle, in the very upper part of the mantle. And the zone that the tectonic plates are made from is the lithosphere, as I said. Number 6, what are the 2 types of crust? So there are 2 types of crust we see on Earth, that very thin, rigid layer at the surface. One is oceanic crust, and it is fundamentally different than continental crust. So if we think of our igneous rock lab, the oceanic crust is made of basalt, whereas the continental crust has much more felsic rocks in it, granite, rhyolite, andesite. So those rocks are less dense, and that's why the continents float up above They're more buoyant in that mantle, and the oceanic crusts that are basalt gabbro, mafic rocks, iron and magnesium heavy, lower silica, they sink. And that's why all the water goes into the oceans, because those rocks are lower. So the water is flowing into the lower parts of of Earth. All right, number 7. Name 3 sources of Earth's internal heat. So you can go ahead and click into that and answer that question. And you'll find that the sources of Earth's heat really are threefold. Extraterrestrial impacts, those collisions created heat that was accumulated in Earth. Gravitational contraction, as the planet formed, it keeps contracting in due to gravity. That also adds heat to the system, as well as radioactive decay of those radioactive elements that are, as they decay away, each one of those reactions releases energy. Number 8, which process is still producing heat within the Earth? It's that radioactive decay. We still have radioactive decay happening. Don't have a lot of extraterrestrial impacts anymore, not on human lives anyway, scale. And gravitational contraction is pretty well complete. Number 9. So there is a video there. Let's see. Oh, there's our crust, continental crust, oceanic crust, and the upper mantle. All right. Sources of heat energy within the Earth, those extraterrestrial impacts, gravitational contraction, and the decay of radioactive elements. So here we have some potatoes boiling. And these potatoes give us a sense of convection currents in the mantle, whereas those potatoes that get warm right in the center of that pot rise, and then they go out to the outside of the pot. They cool off once they get to the surface. They sink back down. They get close to the burner. They heat, and that sets up convection cells. So what is causing those potatoes to rise in the middle and sink at the sides? Convection. All right, number 10. The same thing, this convection is happening in the Earth. Hot material that is less dense rises to the surface. It transfers heat to the lithosphere at the surface. Then it cools, because it's at the surface of the Earth, sinks back down into the lower mantle where it heats up because that core is much hotter than the surface of the Earth, and then it rises again. That circular motion, again, just like in the potatoes example, is called a convection cell. And you see that in here with the red arrows. In what layer is this process occurring primarily? And you can see here it's occurring in the mantle. There are also convection currents, separate ones that are occurring in that liquid outer core as well, and those may be responsible for the magnetic fields that we have on Earth. All right, we're moving on now to part 2, seismic waves and the Earth's interior. So if you look at number 11 in your assignment, what are the 2 main types of waves? Surface waves and body waves, okay? So surface waves and body waves. Body waves have a subcategory of P waves, meaning primary wave, and you notice that is the first to arrive. So this right here that you're looking at is actually a seismogram recorded in the United Kingdom from a distant earthquake, and there's seismograms located all over the Earth. Recording all the seismic activity around the globe, and anywhere on Earth, those seismograms can pick up the waves that are released when an earthquake happens, which an earthquake is when there's movement along a fault between rocks, sudden movement caused by plate tectonic motion. So what happens is the time starts at the left. You can see that in the lower axis right here, time in hours, minutes, seconds. And as an earthquake is coming in, or if there's no activity, it's just a flat line, then what we have is the very first wave from any given earthquake comes in. That's the primary wave. It's a body wave. It's the P wave right here, right there. The second wave that's going to hit is bigger amplitude, and that's called an S wave. And S stands for secondary wave. So that's the second wave to come in. The next set of waves are over here, and this is when the amplitude gets really big, and those are the surface waves. Those are the surface waves. So we're going to spend some time talking about what those waves do and what their motion is like. All right, so moving on. All right, in number 13, where do those surface waves travel on Earth after an earthquake? Those travel on the surface of the Earth, whereas the body waves are called body waves because they travel through the body of the Earth. Number 14 in your assignment, when an earthquake happens anywhere on Earth, what waves are produced? Again, going over this again, body waves, P waves, S waves, and surface waves. All right, we're going to start by thinking about surface waves, okay? So let's look at surface waves here first. Number 15 in your assignment, and you can see surface waves have two types of waves. One is called a Rayleigh wave, and the other is called a Love wave. And these diagrams here show you which way the particles move when a surface wave, a Rayleigh wave, or a Love wave comes through them. So the direction of propagation is from left to right, and you'll notice that bump here, t minus t equals 1, time 2, and time 3. The particle motion is very similar to the particle motion in waves along in the ocean. Like if you're at the beach and you stay you're good and you're in the waves, your motion is going to be very similar to this in a circle as waves pass through you. Okay, Rayleigh waves. Okay, now so the other one is the Love wave, and notice the particle motion on the Love wave. Those actually, the direction of propagation of the wave from left to right, but the particle motion is actually back and forth, back and forth. So number 15 in your assignment, which surface wave moves the ground from side to side, looking only at the particle motion? So on the Rayleigh wave, it's in a circle. On the Love wave, it's side to side. So number 15 is the Love wave, moves it side to side. And it was named after Mr. Love and Mr. Rayleigh. So, all right, now, which surface waves will arrive first after an earthquake? The answer is the Love waves. The Love waves move faster. They will arrive first after an earthquake. And number 16, which surface wave moves the ground in a rolling motion? And that's the Rayleigh wave. All right, let's look at body waves here. So body waves are P waves and on the left-hand side, and S waves. Remember, they're named for primary waves. S waves are secondary waves. And let's think about how these waves move. So P waves are compressional waves. So they move like a slinky moves. They travel through both solid and liquid rock and are refracted at boundaries between liquids and solids. So the P waves move also faster than the S waves, as we noted from the seismogram, that they are the first to arrive. The S waves are secondary shear waves and only travel through solid rock. They do not travel through liquid, which really isn't surprising. Liquids have no shear strength. Okay, so if you try to shear a liquid, it has no shear strength to hold on. So they absolutely stop like a block when it hits any kind of liquid. S waves are also a bit slower than P waves, which is why they're the secondary wave and the second ones to arrive at the seismograms once an earthquake has happened. All right, so number 17, which body wave moves the rock in a forward and backward motion by compressing the solid material? So if we look at the particle motion over here, the blue, like a slinky moves, if you guys know what a slinky is, the compressional wave, the P wave is the one that is compressional and material moves back and forth. Number 18, which body wave moves the rock in an up and down motion in a shear sense? An up and down motion here. The S waves show us that particle motion that's up and down in a shear sense. All right, which body wave appears first after an earthquake? Again, it's the P wave, not the secondary wave. Okay. And here we go again, just a reminder, body waves and surface waves, the primary wave is first, the S wave, secondary wave is second, that's the shear wave. The P wave travels through both liquid and solid, but if it's going through solid and it hits a liquid boundary, at boundaries, it refracts. And we'll see an example of that in a minute. The S wave, when it gets to a liquid, a boundary between a solid and a liquid, it absolutely stops. S waves cannot propagate through liquid at all. And the surface waves, those big amplitude, super dangerous waves that we see after an earthquake, those travel only on the surface of the earth. They do not propagate through the body of the earth. All right, so how do we know about these layers? We talked about the layers of the earth, the crust, the mantle. The crust, the mantle, the outer core and the inner core, and then separately we talked about the zones, the lithosphere and the asthenosphere. How do we know about those layers? And we're going to talk now about the crust, the mantle, the outer core, and the inner core. How do we know that? And we know it because of this seismic data. We can...
All Seahawks. Teachers, please tune in to the Seahawks Scoop.
We can look at those layers and find that we can look at all the seismic data, the P waves, the S waves, and the surface waves, and mostly the P waves and the S waves, and we can see those layers from that data. All right, I'm going to leave this video. It's linked in your document, and you can watch this on your own, but it does help explain all of this. All right, so here, let me walk you through the rest of this assignment. And so here's a picture that's in your assignment, and this is a picture of the Earth with seismic stations. So there's a little person at each seismic station. We have an earthquake right over here, earthquake 1 on your document, and these are the P and S waves. So the P waves are the blue waves, the S waves, the shear waves, are the pink wavy lines. And we can see here the pattern of how they propagate through the body. Remember, these are body waves and they propagate through the body of the Earth. And we have our layers. So it was maybe like 1904, I think, when seismologists and scientists started to see this pattern. They started to look at earthquake data from around the world. They had seismograms, and they were seeing, gosh, we see these patterns, like there's these weird refractions and we lose the S wave, and what is that telling us about the interior of the Earth? And they knew the physics of these waves and how they propagated, and that gave them the information they needed to start to construct this model of the Earth and the layers of the Earth, even though, of course, we can't drill in. I think the deepest drill in right now is maybe like 10, 13 kilometers. I mean, remember, continental crust is an average of 35 and can be as thick as 70 kilometers. We can't even get through the crust in terms of drilling. Like, there is no way we can get into the deep mantle, even the upper mantle, or the core. We just can't do it. It's too hot down there. The drill bits just fall apart. Like, we can't, they melt. I mean, we cannot, We cannot drill. We don't have the technology yet. Maybe someday, but not even close yet. All right, so let's talk about, we have to learn about these layers in some other way. And these P and S waves, these seismic waves, give us a view into the body of the Earth. So we're right now on number 20 in your assignment. And just a reminder, as we look at this document, which body wave, those are the P and S waves, which body wave travels only through solids? And the answer is the S wave. And you can see that in here, the pink wavy lines. Look, as soon as they hit the outer core, which we now know is liquid, they don't propagate anymore. They just die. If you look at this one right here, they stop. They do not propagate through any kind of liquid. And what people were noticing is, there they are. So there's this interesting shadow zone all on the back side that the outer core causes. And there's no S waves on the back side of the Earth if an earthquake starts over here. No S waves. It's called the S wave shadow zone. So number 21, which body wave travels through solid and liquid? The P waves travel through both solid and liquid. Going through solid here, everything's fine. Now, once it hits a liquid, a boundary between a solid and a liquid, it refracts. So it changes direction, okay? And because of that, we end up with a P wave shadow zone, where we see very weak or no P waves because of that refraction as it hits the boundary between the solid and the liquid. Number 22, for P waves, what happens when they hit a boundary? Again, they refract, and here's the example of it right here. Number 23, why is there a shadow zone for S waves? There's a shadow zone for S waves because they do not travel through liquid. And here's where we're seeing that outer core is liquid. The S waves cannot travel through it. Number 24, why is there a shadow zone for P waves? And again, because of the refraction. So it can go super close, not quite hit the boundary, travels fine in its normal straight line. And once it hits the wave right next to it, hitting that boundary is going to refract, and you get this P wave shadow zone. Number 25, which shadow zone is bigger, the P wave or the S wave? The S wave shadow zone, because they don't travel at all through liquid. The P wave has one on either side of the Earth over here. Same thing happening. Number 26, if there's an earthquake at location EQ1, so location EQ1 right here, what waves will you see at location A? So in your document, you see A is right here. This is the A station. You will see both S and P. And then as you go around the Earth, and I'm going to let you finish this up on your own, on your document, there's station B, station C, station D, and station E. But as you go around the Earth, here, over here at B, if B is right here where this person is standing, you are going to see no S waves and no P waves. So only surface waves. Don't forget the surface waves. The surface waves are going to travel all the way around the surface of the Earth, all the way back to the original location. So those surface waves are always present at every single station. So you're always going to see surface, and the question is, when are you going to see S waves and when are you going to see P waves? All right, now number 31 I have in here with the seismogram. If this is in your assignment, number 31, what is the first wave to arrive? Again, we're just reiterating what we talked about before. The P wave is the first to arrive. The second wave is the S wave, both body waves. What are the last waves to arrive? The surface waves. And the last question, number 34, surface waves are the most damaging waves to the property of an earthquake. Why do you think that is? Oh my gosh, look at the amplitude. look at the amplitude of those surface waves. That motion is definitely gonna hurt some buildings and some structures that we have. Okay, so go ahead and finish up your assignment, and thank you for watching this.